we continue with our discussion on the synthesis of synchronous sequential circuits, which we have started in the last lecture. So, we continue with our discussion in this second part of this lecture, part 2. Now, before we start, you recall in the last lecture we mentioned the different steps that you need to go through to synthesize or design a synchronous sequential circuit. The first step is most important, is to capture the behavior from some specification. It can be a textual specification, it can be any kind of specification. You may be having some idea in your head, you are trying to capture it, or there is some text which is written, from there you are trying to capture the behavior. So, you are trying to capture the behavior and you are trying to formalize it by expressing it in the form of a state table or a state transition diagram. Now, in this lecture we shall be spending some time specifically on this part of the entire flow, that how to construct state transition diagrams and state tables starting from specifications. So, we concentrate on state transition diagrams and state tables in this lecture. So, here we are going into a little more detail. So, here although we have mentioned this, I am repeating. A state transition diagram, when you say, it is actually a graph. A graph contains some vertices and edges. It is a graph which specifies the different states of the finite state machine, the different conditions or the inputs under which the state changes will occur, and also the output values that will be generated. So, the state transition diagram captures the whole behavior of the FSM. Now, notation wise, the states, they are denoted as circles and they are typically labeled with unique symbols, so that you can distinguish one state from the other. Well, in the early example we saw in the last lecture, we labeled the states as A, B, C, D. Okay? Fine. Now, there are states, there are also transitions. For example, this is one state, this is one state, they are labeled with A and B. There can be a transition between A and B which is denoted by a directed edge, an edge with an arrow. These are called transitions. They are represented as directed arrows between a pair of states. Well, these arrows can be self loops also. So, a state and itself, it can also be like this, and each transition is labeled by two numbers alpha and beta, where alpha denotes some input combinations and beta denotes an output combination. So, if I write here alpha comma beta, it indicates that if you are in state A and input alpha has come, then you go to state B and generate the output beta, right. This is what the interpretation is. Now, as we had said, we shall again see examples. State table is an alternate depiction of the state transition diagram. It is not something separate, they represent the same information. Instead of showing it in a diagrammatic form, you show it in the form of a table. That is the only difference. Okay. So, in this table, just like in the diagram, for every value of the present state, here the next state is specified and also the output values for each input combinations are specified, right. So, these we will see, we will take a number of examples. So, the first example, let us take this is a very simple example. The example goes like this. This is a very simplified form of a traffic light controller. This is nowhere near to a traffic light controller, but something similar. The only similarity is that there are 3 lamps, red, yellow and green. Nothing else is similar from a traffic light controller. Okay, here the problem specification is like this. there are 3 lamps, red, green and yellow, that glows cyclically. That means, first red, then green, then yellow and again back to red. And let us say with a fixed time interval, let us say 1 second. Now, this time interval we are not really bothered about, because we will assume that our circuit is like this. There is a clock. If I need a 1 second period, then I will be applying a 1 hertz clock. So, changes will happen every 1 second. There are no other inputs. There are no other inputs in this circuit and the outputs are red, green and yellow. Okay. Now, first thing is that how to represent this problem in the form of a finite state machine. First thing is that let us define the states. There will be 3 states corresponding to the 3 lamps that are glowing, red, yellow and green. The arrows will indicate state transition, red to green, green to yellow and yellow to red. And the other thing we are assuming is that there are 3 outputs, red, green, yellow. Let us assume in this order. So, when you are in the red state, this line will be 1, this will be 0, this will be 0, which means red is glowing. If you want to grow green, this will be 1, this will be 0, this will be 0. And if you want to glow yellow, this will be 1, this is 0, this is 0. So, now you can understand, you see there are no separate inputs, that is why the input is shown as empty, phi means empty. So, when you are in the red state and a clock comes, you go to green, the input is not, the input is phi and the output is 0 1 0. 0 1 0 means green is glowing. Okay. When you are in green and a clock comes, you go to yellow 0 0 1, which means yellow is glowing, and when you are in yellow, you will go to red 1 0 0 means red, and this goes cyclically, right. And you see, because there are no inputs, the states directly determines what the outputs will be. So, this is like a Moore machine. The output depends only on the state, it really do not depend on the applied input. Okay. So, talking about the state table, here this is a very simple problem. So, state transition diagram is shown on the left. On the right side, I am showing the equivalent state table. So, broadly there are 2 columns I had shown in the example earlier. One is for the present state, other is for the next state and outputs. Because there is no inputs, there is a single column in the second part. The present state, if it is red, then the next state will be green and the output will be 0 1 0. Now, if the present state is green, next state will be yellow, output 0 0 1. If it is yellow, next state is red, output is 1 0 0. So, exactly what this state transition diagram is specifying, right. So, let us move on to slightly more complex problems to see how the state transition diagram and the state table can be constructed from there. Let us see. Okay. This is a slightly more difficult problem. This problem is that of a serial parity detector. So, what is this problem? You first look at this circuit. This circuit is having an input x and an output z. So, x is applied with a serial bit pattern, let us say 0 0 1 1 1 0 1 0 0 1, something like this. And output also will be generating a continuously bit pattern something like this. So, what will it indicate? This will indicate the parity of the input bit stream. So, if you just write down this bit stream one below there to be clear, let us write it here. Let us say this is 0 0 1 1 1 0 1 0 0 1. Now, parity means with the number of ones whether they are odd or even. If it is odd, I will be outputting 1, if it is even, I will be outputting 0. Let us say that is our convention. So, we will be looking at the number of bits that we have seen so far, and whatever is the parity, the output is set accordingly. Okay. Let us start. This is my input x. So, what will be my z? Even, a 1 has come, it is now odd parity. So, again a 1 has come, it has become even. Well, again a 1 has come, it has become odd. 0 has come, it remains odd. There is a 1 has come, it has become even again, 0 again even, 1 again odd. So, this will be the output, right. So, in this problem, this x is the single input, z is the output, of course, there is a clock. If you think of the state, what are the things you need to remember? You only need to remember one thing. What was the parity till now? Was it odd or was it even? This you can represent by a single bit in 2 states. Let us name the 2 states as even and odd. So, the corresponding state transition diagram will look like this: even, odd. Let us say even is the initial state. So, if a 0 comes, you remain in the even state, the output is 0, but now if a 1 comes, you go to the odd state with an output of 1, and while in odd state, if a 0 comes, you remain odd, output 1, and if a 1 comes, you go back to even with a 0, right. So, from here you can similarly construct the state table. Here you see the second part is little more complex. The first part as usual is the present state, second part is the next state and the output. States, there are 2 states, even and odd. Next state and output, here there will be number of columns depending on all possible input combinations. Because in this circuit there is a single input x and x can be either 0 or 1, there are 2 columns in the second part, one corresponding to x equal to 0, other corresponding to x equal to 1. And whatever is listed here is actually this n s and z, next state and output. So, if you are in even, let us say here, if x is 0, then you remain in even and the output is 0, that means this edge. If the input is 1, you go to odd with output 1, it means this edge. So, like this for all the edges you can see the entries, right. This is actually quite easy to construct. Now, let us look at a slightly more difficult problem. This problem is that of a sequence detector. So, what is a sequence detector? Well, it is something similar to the previous problem in the sense that there is a single bit stream x as input and a bit stream z as output. Of course, there is a clock, I am not showing the clock. Now, in x I am applying a bit stream. Now, whenever this pattern 0 1 1 0 appears, the output will be 1, otherwise it is 0. So, let us take an example. Suppose my input is like this. So, you see this 0 1 1 0 in what places it is appearing. See, one place it is here, one place it is here, and there is a overlapping pattern here. So, I am assuming that overlapping patterns should also be considered. The 0 1 1 0 before which finishes, the second pattern starts. So, in the output there will be a 1 out here, there will be a 1 here, there will be a 1 here, all the rest bits will be zeros. This is the circuit that we want to design. So, this will be my x and this will be my z, right. This is a Mealy machine because there is an input and the output will of course also depend on the input and the state both, right. So, this is not a Moore machine, this is an example of a Mealy machine. So, here is another example, you see 0 1 1 0, there is a 1 generated here, 0 1 1 0, 1 generated here, 0 1 1 0, 1 generated, but here there is no overlap. Okay. Fine. Now, let us see how we can construct the state transition diagram for such a circuit. Before I show it, let us try to work out how it should be. Okay. Let us see. Fine. This is what the final solution is shown. Let us try to understand why we have gone for this, because we want to detect the pattern 0 1 1 0, right. Well, we do not know how many states will be required. So, as we construct, the number of states are getting constructed. See, the first thing is that we start with an initial state, let us say S 0 is my initial state. So, I look for the first 0. So, whenever I get the first 0, I go to state S 1. So, S 1 indicates that I have seen the first 0, this is my state S 1. So, while in S 1, if I see the next one here, I go to state S 2. You see, if I see a 1, I go to state S 2. Similarly, if I see another one, I go to state S 3. I see another one, I go to state S 3. Okay. Now, if I see a final 0, that means I have detected the pattern. So, from S 3, if I get a 0, so naturally I will have to output a 1 because I have got the pattern. Now, the question is where should I move it back? Should I move it back to S 0 or somewhere else? Now, the point is that because we are allowing overlapping patterns, so let us consider an overlapping pattern like this. So, this was 0 1 1 0, there is an overlapping 0 1 1 0. Now, when you are in S 3, you are in S 3 means what? You are here, you are at this point, right, you are S 3. Now, a 0 has come. Now, this 0 is also S 1 for the next pattern. So, instead of moving it back to S 0, we are actually moving it back to S 1, because you need also to check the next overlapping pattern and it may start here also. So, you are actually in S 1 for the next pattern, and for the other ones I think it is quite simple, because in S 0 if you get a 1, that means you are trying to detect 0 1 1 0. If you get a 1 in the beginning, you remain in S 0. Now, in S 1 you have detected a 0, but if you get another 0, no problem, you are still in the first 0, you remain in S 1. But in S 2, that means you have got a 0, a 1 and again a 0, this can be the start of a 0 1 1 0. So, you have to go back to S 1. Similarly, from S 3 to S 1, and in S 3 if you get a 1, which means it is a 0 1 1 1. So, it is not the pattern, you have to go back to S 0 and start from the beginning. So, you see drawing this diagram is not trivial, you may have to think a little bit, consider all possibilities and then come up with the diagram, the edges. Okay? Fine. Now, once you have drawn the edges, the rest is fairly straightforward. There I have not shown the state diagram there. Let us take another example, state table I mean. Here in this example, we consider, say if you look at the previous example, just a second. This was the example of a sequence detector. Just one thing let me tell you before we move on. So, if you want to construct the state table which I have not shown, there will be two parts to it. The first part will be the present state, there will be 4 states S 0, S 1, S 2, S 3, and in the next state, because there is only one input. So, there will be one corresponding to x equal to 0, one corresponding to x equal to 1. Okay. Just like that serial parity detector, same kind of table will be there, there will be 4 rows here, right. Okay. Now, we consider an example which is a serial adder. Now, I took this example earlier when we were discussing about the flip flops and the other simple applications of flip flops. Now, let us look into the design of the serial adder in a little more formal way. Now, I mentioned earlier, if you recall, that a serial adder, this is a serial adder, is a circuit which will be having 2 serial inputs x 1 and x 2, where the bits will be coming serially and the sum will be generated z serially in synchronism with a clock. So, when you add two numbers like 0 1 0 1 1 and let us say 0 0 1 0 1, 1 1 is 0 with a carry of 1, 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 1 with a carry of 0. Now, initially carry is 0. So, you see, for a serial adder, if you think what should be my states? For addition, the only thing that I have to remember is the carry from the previous stage. So, that will be my state, the carry. There will be one state variable. So, there will be two values 0 and 1. So, in this diagram I am representing them as two states A and B, where A represents carry 0 and B represents carry 1. Now, let us see how this state diagram works. So, when you are in state A and you have got an input 0 0, 0 0 and no carry. So, what will happen? The sum will be 0, sum is z, sum is 0 and you remain in A, means the carry remains 0. So, if you are applied 0 1, sum is 1, no carry, remain in A. 1 0 same, sum is 1, no carry, but when you get the inputs 1 1, then this sum will be 0 and there will be a carry of 1. So, now the state will change from A to B, B indicates carry 1, and while you are in state B, the things are similar. So, if you have input 0 1 with a carry 1, then the sum will be 0 and carry will remain 1, 1 0 also sum will be 0, carry 1, and if it is 1 1, sum will also be 1, carry will also be 1. But only when the inputs are 0 0, there will be no carry. So, you move back to state A, but this sum will be 1. Okay. So, just you see and think how the process of addition goes on, and you can get the behavior of this serial adder in terms of the state transition diagram. Okay. Fine. Now, from the state transition diagram, you can construct the state table, same thing. So, here you see there are two inputs, right, x 1 x 2. So, in this case, in the second part there will be 4 columns, one corresponding to the input combination 0 0, 0 1, 1 0 and 1 1. The rest is same, exactly what this diagram shows. So, you are in state A, the input has come 0 0, you remain in state A and the output is 0, okay, like that. The same thing you can capture it like this. Let us take another example. This is an example of a counter. Well, we shall be looking into the design of counter in more detail later, lot of different kinds of counters we shall see, but let us look into an example right here. This is a 3-bit binary counter. So, what does this counter do? This counter is supposed to count in the sequence 0 0 0, 0 0 1, 0 1 0, 3, 4, 5, 6, 7 and then back to 0. Now, the counter is a circuit like this. Counter does not have any input externally, there is only a clock and the outputs are generated in synchronism with the clock. The count value 0 0 0, 0 0 1 sequentially they will be generated. So, there is no separate input. So, the state diagram, state transition diagram is very simple. There will be 8 states, I am calling them S0 to S7. Well, I am just for convenience, I am considering the binary equivalent, the decimal equivalent of the binary combinations and I am encoding states like that. For example, S6 means this 1106. Okay. So, when you are in S0 and the clock comes, no input phi, you move to state 1, your output is 001, that means now you are in 1. From S1 you move to S2 010, 2, S2 to S3 011, S3 to S4 similarly, S4 to S5, S5 to S6, S6 to S7 and S7 back to 0, 0 0 0. So, the state table is also quite similar. These are the present states, there are 8 states and for each of these states there is no input. So, there is a single column here. So, you show that what will the next state be, S0 will go to S1, S1 will go to S2 and what will be the corresponding outputs, right. Same information you are depicting, okay, fine. So, let us take one last example. This is a slightly more complex kind of a counter. This is also a binary counter, but it does not count in the binary sequence. So, what it says is that this is a 4-bit counter that counts in the sequence first 0 0 0 0, then 0 0 1 1, then this, then this, then this. So, there are 6 states and then back again to 0. So, you see I have just again used the decimal equivalence of these states S0, S3, S6, S12, S9, S12, S10 and then back to S0. This is my regular sequence of counting and the state transition is exactly labeled in the same way as in the previous example. So, S0 to S3 it is labeled by 3 0 0 1 1, there are no inputs, S3 to S6 labeled by 6 0 1 1 0 and so on, and X10 back to S0, this of course is missing, it should be phi 0 0 0 0. And it also mentions if the counter starts whenever you switch on the power, if it starts with any of the other states at the next clock it should go to 0 0 0 0. So, if it is in any of the other 10 states out here, so all of them I have shown only 2, that is dots. So, there will be arrows from all of them. So, you will be going to S0, right. So, if we have a specification like this, from there you can also construct the state table same way, and from the state table you will be moving into the next step. So, here we have looked at a number of examples for constructing the state table and the state diagrams. Now, with this we come to the end of this lecture. Now, from the next lecture what we will see, we shall look at some of the examples and try to go through the entire flow of synthesizing a synchronous sequential circuits. So far we have only seen how, starting from the behavior, we can construct the state transition diagram and the state table, but the remaining steps we shall be learning in our next few lectures. Thank you.